So, today we will start with one of the most important analog signal processing block, that is multiplier. After discussing about amplifiers, it is appropriate that we now go to from linear to nonlinear operation. The most important nonlinear operation that analog signal processing has is multiplication. Okay. So, we will consider now what are the various means of multiplying using IC components, basic techniques. First of all, let us try to understand the basic definition for a multiplier. What is a multiplier? So, V naught is the output. This should be a function of two inputs Vx and Vy. This is what basic unit doing multiplication should do. That is, it should give an output which is a function of two inputs. In general, therefore, anything, any nonlinear device is going to give us an output which is independent of Vx and Vy, and that we will call as V. What will it be? It is called offset, because that is independent of Vx and Vy. Then some term which is purely dependent upon Vx. This in multiplier terminology is called x feed through. It should not come, right, but if it comes, it is called x feed through. Then obviously what else will be there? Ky Vy, which is obviously called y feed through, and then we have K naught into Vx Vy, and then we have obviously Vx squared, Vy squared, Vx squared Vy, Vy squared Vx. These are called the nonlinear terms. Okay. That means this particular output is going to be there in almost all nonlinear functions, right, in general. Only thing is, in certain nonlinearity we may have V offset becoming naturally 0, in another nonlinearity Kx Ky may be naturally 0 and Fn naturally 0 kind of thing. That means, we must devise a configuration wherein this is as small as possible, these two are going towards 0 and this is as small as possible. That is a good configuration for the operation of multiplication. That means, a non-ideal any multiplier, practical multiplier will be non-ideal obviously. That means, all these components are likely to be present in some measure, even if the best configuration is available to you. Okay, these non-idealities will be small, but they will be present. So, in a precision multiplication operation, it is your duty to see that there must be some possibility of adjusting this to go towards 0. Okay. So, let us see, if you select a configuration wherein this itself is going to be very small, that is the proper configuration for multiplication. Okay. So, this has to be made as small as possible. Using the nonlinearity of the device, you try to put it in a configuration that this is made as small as possible. Then how do we make basic adjustments of a multiplier? We see to it that K naught is equal to, is standardized in most of the precision multipliers as 1 over 10 volts. So that the multiplication operation is possible over a dynamic range of less than or equal to 10 volts, less than or equal to, greater than or equal to minus 10 volts. Similarly, the Vy should have a dynamic range. This is the standard for precision multiplier design. Okay. That means, the constant has been adjusted constant of proportionality has been adjusted to be 1 over 10 volts, and V x and V y must have a dynamic range of minus 10 to plus 10, and then the symbol for the multiplier becomes that is the block, this is V x, this is V y, and multiplication operation, okay, and this is V naught, and this is nothing but V x V y by 10. So, it is automatically assumed that if you are using a standard IC multiplier and these outputs are given, you can take for granted that the constant of proportionality, okay, K naught has been adjusted to be 1 over 10 volts. So, this is basic to the design of IC multipliers. Okay. So, you can keep on connecting one multiplier output to the other, and it will be perfectly compatible because everything has been standardized. You can see that if K naught is equal to 1 over 10 volts, the maximum output ever of this multiplier will be 10 volts. Okay. So, these are compatible with one another, therefore, you can connect these multipliers in cascade without any problem of dynamic range. Okay. So, obviously, this requires that before you use any multiplier, you must see to it that these non-idealities go towards 0. Now, how do you make the adjustment? The adjustment is done this way: V x is made equal to 0 volts, V y is made equal to 0 volts, then only output that you can have is the offset, and that is adjusted to be equal to 0 by what is called offset adjusting methods. Okay. So, V offset is made equal to 0, this is made to go towards 0. Then we make V x equal to 10 volts, V y equal to 0 volt, then any output if it comes, it must be due to x feed through, okay, and that will be coming through as its maximum error output. Okay. That has to be adjusted to 0, not by adjusting V x, by adjusting a means of making K x equal to 0. So, K x adjustment is done that way. Then V x is made equal to 0, V y is made equal to 10 volts. Output that can now come is due to y feed through, and therefore, it is K y which is adjusted towards 0. Finally, V x is made equal to 10 volts, V y is made equal to 10 volts, and V naught should be adjusted to be equal to 10 volts. Okay. That is, K naught is going to be then adjusted to 1 over 10 volts. Is this clear? When V x is equal to 10 volts, V y is equal to 10 volts, V naught should be 10 volts, then only K naught is going to be equal to 1 over 10 volts. So, when all these measurement adjustments are made, then the multiplier is ready for use, not before that, if it is precision multiplication that you want. Okay. So, you can see that unlike the amplifier, wherein output is only a function of one input, wherein you have just offset and K x times V x and then nonlinearity coming into picture. Okay. Here you have more number of adjustments to be made because it is a function of two inputs. Okay. So, now after this adjustment is made, the multiplier is ready for use, and thereafter you can use the expression that V naught is going to be equal to V x V y by 10, and this is going to be valid for V x and V y both ranging from minus 10 volts to plus 10 volts. This you should remember as the property of a precision multiplier, okay, available in an IC form. Now, this has to be implemented. The circuit implementation of this operation is what we are going to discuss henceforth for some time. What are the basic methods of multiplication? Now, we will consider this devices that are available to you. Let us see. The devices that are available, nonlinear devices that are available to us are bipolar transistors and MOSFETs. These are the devices that are available. Bipolar is essentially a nonlinear device which is using what? Exponential relationship. All of you know this, right? I is equal to I A naught exponent q v by k t minus 1, right? That minus 1 can be. So, exponential current and voltage are exponentially related, and MOSFETs square law. In our previous lecture on voltage dependent transconductance and current dependent transconductance, we have established that these are the complementary things available in nature, okay? And these can evolve naturally as the devices that are necessary for an engineer to complete the whole process of voltage dependent transconductor, current dependent transconductor, that we have established. Obviously, a multiplier is nothing but can be thought of as a voltage dependent or current dependent, okay, amplifier of a sort. Okay. So, we have to obviously use these two relationships. Let us now see how we can use these relationships in formulating a multiplier. First, the basic multiplier application using bipolar device will naturally use the most commonly known knowledge about multiplication operation using log antilog table. You have been using log antilog tables for multiplication. Once we have a device which can do log operation and antilog operation, obviously we can use it for multiplication by taking the logarithm of Vx and taking the logarithm of Vy and taking the logarithm of 10 volts or V reference we will call it, adding log Vx plus log Vy minus log Vref or log 10 volts, okay, is now going to be the multiplication operation of Vx Vy by Vref. Log of that is what you have got. You have to now take antilog, you will get the multiplication. So, this multiplication or multiplier is called log antilog multiplier. Okay. Then obviously, we know that the transistor transconductance, bipolar transistor transconductance is dependent upon its operating current. This current in turn can be made to depend upon voltage. So, you can now design a voltage dependent amplifier which can be a candidate for multiplication. So, the second property that we will use is transconductance type of multiplier. These two essentially make use of the property of the bipolar transistor for its exponential function, right. The third one on the other hand is the basic principle that we had again learnt, that when I have a switch which can connect V x, okay, or disconnect V x, connect V x or connect minus V x for respectively tau and t minus tau. I can get an average which is V x tau by t. This we have discussed in switched mode regulators, power supplies. And therefore, by making tau dependent upon another voltage now tau by t, by what is called designing a pulse width modulator, I can design a precision multiplier. This is called, okay, pulse width and amplitude modulation type of multiplier. Now, finally, the other device, that is the MOSFET, basically uses square law relationship, and if you have square law relationship, okay, you can devise multiplication by simply what? One technique is, okay, x plus y whole squared minus x minus y whole squared is nothing but, okay, this will be respectively V x and V y. So, what is it? 4 x y. That means add two voltages, square, subtract these voltages, square, and then. So, this is the basic principle of most of the transconductor types, okay, which can be used for multiplication in MOSFET devices, okay, which have large dynamic range. So, we will discuss all these various types of multipliers one after the other, okay, and see how these can be implemented in an IC form. Okay. First, let us therefore take this log anti-log multiplier. So, obviously, we have to perform this log operation and the anti-log operation and add. For performing the log operation, we know that we can depend upon the operational amplifier, okay, to convert voltage into current, because we want a relationship between voltage and voltage ultimately. So, this V x can be converted into current by making it flow through this, right, as long as it is used in the negative feedback mode operation. This is going to be virtual ground. There should be negative feedback from the output. That way, then the current in this is going to be what? V x by R x. Now, let us see. This current has to flow through the collector of a transistor, okay, that this will be forced through the collector of a transistor. Then, if it is still a negative feedback configuration, this will force itself through the collector in order to generate a voltage, which is, what is the voltage generated here? V b is going to be V t log, okay. This voltage is going to be V t log, okay, V x by R x I a naught, right, because of the exponential relationship, okay. So, V x by R x is going to be the current flowing through this, and in order to develop that current, the voltage here is going to be, let us say this is T 1, V t log V x by R x. the output voltage will be negative here, right, with respect to ground. But there should be a connection to the op amp. I can connect it here, still it works. But okay, if I connect it through a resistance here like this, it can still work, okay, no problem, because this voltage will adjust itself so that this voltage is what it is. So, this is the negative feedback, right. So, why would I put a resistance like this? I can even connect it like this. Here I am trying to discuss both. This is called a log amplifier. Okay. What we are now designing is nothing but a log amplifier. Given the input voltage Vx, it is going to give an output here which is nothing but minus Vt log Vx by Rx IE naught, right, whether you put a resistance or not. Why should there be a resistance put? I say it is safer to put a resistance. If you do not put a resistance, okay, let us see. No, it is going to be, nothing is going to happen, because current is going to be limited to Vx by Rx. Okay. Voltage will adjust such that, okay, this current is made to flow. You can look at this structure itself as a negative feedback amplifier now. This is an inverting amplifier, okay, here to here, and then you have a transistor amplifier in common base, which has, if you ground this basically, which has a gain of its Gm, which is 1 over Re, times Rx, and that output is connected to the op amp. That means, the open loop gain of this, let us say, is A, that is to be multiplied by Gm into Rx. That means, overall loop gain has increased in this negative feedback situation, right, from A to A into Gm into Rx. So, if your op amp has been designed with just unity gain kind of operation being satisfactory for frequency compensation, right, then it may fail, because now the open loop gain is more. Okay. That means, the frequency compensation capacitor might have to be further increased, because the open loop gain is increased. We do not want therefore to put some other frequency compensation here, or we would like to use the same old frequency compensation, then this kind of feedback must be given without the gain being increased. So, we put purposely emitter degeneration resistance. So, we will increase the emitter resistance by putting, okay, additional resistance here, so that the gain now is Rx by Re, small r e plus Re1. So, you can reduce the gain to almost nearly 1, and therefore, resurrect this amplifier, okay, which was going to oscillate otherwise because of its inherent frequency compensation being valid for its own loop gain of maximum loop gain of A. Okay. So, this I can make it, you may think, as high as possible, but that is not so. If I keep increasing this, the voltage at this point will keep increasing to a value which is Vx by Rx into Re. That might go towards supply voltage, okay. And therefore, I should be very careful in limiting this to a value such that the output of the op amp does not go to its saturation value. Okay. So, these are the conditions for selecting the value of R. This is the case with even design of a log amplifier. Okay, if you want. Now, we have got the required voltage. Now, what should I do? I should add to this voltage the log of another voltage which is V y. That again is going to be similar to this, right. So, I will take another voltage here that will be R y, this you get V y, and the input current now here in this is going to be V y by R y, and that again has to be converted into and adding requires, you might think, another amplifier. It does not require, because we have a voltage here, we have to put in series with this another voltage, right. So, which will correspond to same thing, but determined by this current. That means, I will now have this coming like this, that is all, right. I am forcing V y by R y through the other collector, then automatically this voltage gets developed, but still I have to complete the negative feedback. So, once again I will put what R e 2, so that there is negative feedback for this. Is this clear? So, ultimately now we are getting a voltage here at this point, which is nothing but this point output, let us say we are taking, that will be nothing but minus V t log this minus V t log V y by R y I e. This is the output at this point. Is this clear or not? Now, we have got this such that now the output is going to be equal to minus V t log, what is it, V x V y divided by R x R y I e naught squared. So, we have multiplied V x and V y. Only thing is, in our method of multiplication, we would like to now subtract from this, or we have added these two negative voltages. That means, we have to subtract from this another similar term which is dependent upon V r. So, for that purpose again we will use a similar technique of converting. So, let us see what we are going to do. We are going to use therefore another transistor similar V r, we call it. What will be the current in this? Let us call it R r here. So, V r by R r, which will flow through this and establish a voltage corresponding to again minus V t log V r by I e naught R r. So, what happens here now? We have already developed with respect to this a negative voltage, another negative voltage we have developed corresponds to what? Minus V t log V x V y by R x R y I e naught square. These are the two negative voltages we have developed with respect to ground. That means, if you take this differential voltage, it is subtraction of this voltage from this voltage. Is this clear? Which will again form what? The input voltage to another transistor base emitter junction. Is this clear or not? This will form an input voltage to another transistor base emitter junction, right. This is more positive than this, right. This is minus 2 V gamma kind of thing, this is minus V gamma kind of thing. So, now this will form the input voltage. What is the input voltage to this? Actually it is minus V t log, okay, V r divided by I e naught r r plus this minus this, right, V t log V x V y I e naught squared r x. Is this clear? Circuit is not complete, okay, because we have been able to establish this, and obviously there should be negative feedback there, which means there should be a resistance to this, right, which we will call this as T4. So, we will call it as RE4. So, as far as this is concerned, it establishes the voltage. So, now everything is clear, and we have been able to apply this voltage to base the emitter junction of a fourth transistor, and what will be the collector current dependent on? This voltage. What is this voltage? This is V t log, you just take V x V y by V r, I e naught gets cancelled, okay, R x R y R r, and there will be 1 I e. That is the voltage that you are applying. And what will be the collector current then? If that is the voltage that is applied, what will be the collector current? Exponent of this voltage divided by V t, okay. What is that? V t will get cancelled, exponential of log of that, okay. So, you will get V x V y R r, V r R x R y, I e naught gets cancelled, right. So, I e naught exponent this, right. So, we get here the current which is nothing but V x V y divided by V r R R x R y, that is the current. So, now you see how neatly this is working. This current can be made to go through another resistor of an op amp which is connected in similar fashion. Okay. This current will therefore be converted to a voltage. So, what will be the output voltage now? This is I, okay. This I is flowing in this direction, okay. So, I r, okay. So, which is nothing but, okay, V x V y by V r, okay, and I will make r equal to what? R x R y by R r. Then output will be simply V x V y by V r. So, you get a precision multiplier which is totally independent of I e naughts, right, as long as all the transistors have the same I e naught. That is why this is a very cheap multiplier, okay, precision multiplier, but cheap, single quadrant, because V x V y and V r have been assumed to be positive, okay, so that the current is only in this direction. This is a single quadrant log anti-log multiplier which can operate up to plus minus 10 volts if you design it. So, very simply design of this for its dynamic range is very simple, because you can make this, for example, V x has to go up to 10 volts, V y has to go up to 10 volts, or V x has to go up to 20 volts, let us say, because it is a single quadrant multiplier. We might like to go up to 20 volts, it is simple, and we want the operation of this to be limited to some 1 milliampere, then we automatically know the resistance as 20 kilo ohm. If it is 10 volts, we know resistance has to be let us say 10 kilo ohm, right. So, we can limit the dynamic range of operation of this by limiting the current into this. This is important, right. This current actually fixes up the dynamic range, whatever you want, 20 volt, 20, right. Even you can make it 50 volts, even if the op amps are not working at so called 50 volts, because it is always getting converted into a current. Okay. So, that is why this is also called data compressor, right. Here the voltage can vary by any amount, but the voltage variation here is compressed to something around V gamma. Okay. So, this is data compressor, right, or a compander, right, that is the log amplifier. Okay. So, this is also used for coding purposes, right, because it can exactly compress the data, okay, in a very small range of voltage variation. Right. So, but it can be used straight away for multiplication as also division, because if I make this V x and this V r and the other one V y, it will straight away do division, right. So, this is what is called multiplier cum divider arrangement. V r is what you are calling as your reference, okay, which is going to be maintained constant. So, if you make V r as V y and V y as your V r, you are getting a divider. Okay. And once again division by 0 etc. not allowed, because you cannot go to current which is very low here. Why? Because our assumption is that I e is equal to I e naught exponent q v by k t, not minus 1, that minus 1 has been ignored. So, the exponential operation is necessary, that means current should not be going down to values of the order of I e naught. Okay. So, you are not allowed to make V x or V y or V r equal to 0 in this, even for multiplication operation, not just even for division, right. Even for multiplication operation it will go wrong if the forward current is of the order of I e naught or less. Okay. So, this is a very versatile this thing. Only disadvantage of this is it is using op amps to convert voltage to current, okay, and therefore, the frequency, okay, of operation is going to depend upon the op amp compensation, right. And therefore, it is going to be limited to low frequencies, which is the limiting thing for the op amp. Okay. So, its limitation is only for the op amp, not for the basic idea of multiplication. So, we have just now seen how the idea of log anti-log can be very neatly implemented with the help of matched pair of transistors. Okay. This is obviously a single quadrant multiplier. In fact, we will see later how any single quadrant multiplier can be converted into 4 quadrant by simply biasing it. Okay. So, if you for example, have achieved a single quadrant multiplication, let us say, which is V x V y by V r, that is what we achieved today using log anti-log, but we said V x has to be positive, V y has to be positive, V r also has to be positive or of a single polarity. If you want, you can make all of them work for negative or something, right, but it should be single polarity. Now, if I want to operate with dual polarity input, obviously I will put V x plus some V 1 d c, okay, and V y instead of V d c 1 we will call it as V x 0, V y plus V y is 0, this is a DC, okay, and then make it a multiplier which can work with V x going both plus and minus 10 volts maximum, V y going okay, both plus and minus 10 volts. For that I have to make V x naught equal to how much? V x should be capable of going both plus 10 volts and minus 10 volts, and still the total has to be positive. So, if you make V x naught equal to 10 volts and V y naught equal to 10 volts, which means basically you have to make the log amplifier work for maximum of 20 volts, both of them, right, and apply a DC offset V x naught as an additional current, that is all. Later you will get an output which is going to be, let us say, V x V y by V r, wherein V x and V y can go both plus and minus 10 volts, plus okay, V x naught into V y by V r plus V y naught into V x by V r plus V x naught V y naught by V r. Obviously, these are unwanted terms. These are the two feed through components which have come out. Okay. Because I have introduced a DC offset, we have got unnecessarily V y feed through and V x feed through and DC offset. So, now this is behaving like a non-ideal output, okay, in the case of a multiplier. So, what should you do? You should subtract DC, subtracting that DC is not a problem, okay, it is only a DC, and you already have V y and V x with you, okay. Some portion of V x and some portion of V y has to be subtracted from this. Using op amp, I want you to obtain a generalized what? Single quadrant to 4 quadrant, okay, block. How do you convert? Using op amp, you have V x and V y, okay, V x and V y, you have the log anti-log multiplier, you have the output here, okay, then some portion of V x, some portion of V y you have to take, use all these information and also DC, and then devise an op amp circuit, okay, to get an output which is just V x V y by R. This is the exercise, tutorial exercise I am giving you. Okay. Please carry out this simple exercise using a simple op amp, okay, adder or subtractor. You can obtain this kind of conversion from single quadrant to 4 quadrant. So, that is very simple. That is why nobody bothers whether the initial multiplication, precision multiplication is achieved using okay, transistors in such a manner that you have only single quadrant operation. Okay. Any single quadrant multiplier can always be converted by subtracting the feed through components as well as deducting the offset voltage. Okay. So, please do this homework and come for the next class. Okay. The next type which we will discuss in detail in the next class is obviously one of the most popular multiplier IC multipliers for precision operations, that is called transconductance type of multiplier. Or this is due to, so this is Gilbert's multiplier, right, and we have already discussed earlier what is called Gilbert's gain cell. Okay. What does it comprise? is made up of transistor cell with input coming from two diodes through which currents are flowing. Right. So, this is 2 I naught. Basically, we will have I naught and I naught flowing through this when these two are connected to ground, but let us say we have 2 diodes connected to this, which are forward biased, such a way that the input current to these diodes D 1 and D 2 are respectively I 1 and I 2. Then these are T 1 and T 2 transistors. The currents I C 1 and I C 2, or for that matter current I E 1 and I E 2. This will be related to I 1 and I 2 in the following manner because of the translinear principle. What does it say? We go through the currents, now this and this will add. These two are again getting subtracted. So, I 1 into I E 1 equals I 2 into I E 2. This is from the translinear principle that we have obtained. So, already we know that I 1 by I 2 equals I E 2 by I E 1 from this, or I 1 minus I 2 by I 1 plus I 2 equals I E 2 minus I E 1 divided by I E 2 plus I E 1, which is nothing but at all times equal to 2 I naught. So, we are able to obtain a differential output current I 1 minus I 2 by, if we have this signal itself coming as a differential current signal. How do we achieve that? Using a transconductor, I told you, right. If I can make I 1 equal to some DC current plus V x by R x, I 2 equal to same DC current minus V x by R x, then I can get I 1 minus I 2, which is twice V x by R x, and I 1 plus I 2, which is a DC current. So, for that I use a voltage to current converter with emitters being connected by R x. So, you can see here this current is going to be I naught plus V x by R x, and this is I naught minus V x by R x, and these are flowing through these two diodes which are similar to this. That is the cell. So, what do you get here? I 1 minus I 2 by I 1 plus I 2 is going to be essentially equal to I 1 minus I 2 is 2 V x by R x, and I 1 plus I 2 is 2 I naught. Right. So, this is going to be equal to, let us not call this, this is I naught prime, we will call it I E 2 minus I E 1 by 2 I naught prime, because this current, that is the bias current that is flowing through this, which may be different from the bias current that is flowing through this I naught prime. So, this is important that we are now able to multiply a current with another voltage, and that is appearing as the differential output current. We will repeatedly use this idea of converting voltage to current and doing the current multiplication using Gilbert's gain cell. Okay. We have to also now see how V y can be converted to corresponding current. That also is done, you can see, by using voltage to current converter. So, now I naught prime is going to depend upon V y, and therefore, output differential current is going to be comprising of a product of V x and V y. We will continue further in the next class.